Hello, my name is Vitor and I'm going to present the work Breakup of Thin Liquid Sheet with a Viscous Interface. This work was advised by Professor Márcio Carvalho and Dr. Sérgio Ribeiro during my master's degree at PUC-Rio. Thin liquid films are broadly studied due to their multiphysical aspects. They are found in nature, such as lava flows and avalanche flows, and also in industrial applications like thin film solid-state batteries and printed circuits for low-voltage applications. These examples present a slender aspect ratio, meaning that the characteristic length in one of the three directions is very small when comparing with the other ones. The understanding of thin liquid film stability is of fundamental importance in applications that present such configuration. The occurrence of interface perturbations may affect the stability of thin liquid films. This perturbation may grow due to the action of van der Waals forces and the liquid film undergoes rupture. The rupture dynamics is governed by an interplay between van der Waals forces, capillary forces, and extra interfacial forces. And this rupture process occurs due to the drainage of liquid from the perturbed region, leading to the thinning of the film. This thinning process increases the influence of van der Waals forces on the rupture dynamics. However, the rupture may be desirable or not. In industrial applications such as the atomization process presented by the left figure, the rupture of a liquid curtain into small liquid droplets is desirable. On the other hand, the rupture of the surface film that coats the alveoli in the human respiratory system may lead to undesirable clinical conditions such as the respiratory distress syndrome. So, our goal in this work is to understand the influence of interface rheology on the rupture of stationary free thin liquid films, and more specifically, we aim at numerically address the dynamics of thin liquid films with viscous interfaces, and to do so, we simulate the rupture dynamics of thin films with inviscid interfaces and with viscous interfaces, and then compare the results obtained in both cases. So, our problem is defined as follows. We have a planar flow of a stationary free thin liquid film. The bulk of the film is an incompressible Newtonian fluid. We impose a symmetric perturbation on the free surfaces and consider the effects of capillarity, interfacial viscosity, and intermolecular attraction between the free surfaces through the van der Waals forces. And here we can see the domain of our model. We use the symmetry plane marked by this dashed line to ease the computational cost, meaning that we will only simulate half of this domain. We also organize our workflow in two cases, namely an inviscid interface case and a viscous interface case. We represent the free surface through the sharp interface approach and use the finite element method to obtain approximate solutions for the velocity and pressure fields in our domain. We update the position of the interface through the arbitrary Lagrangian Eulerian method or the ALE method, and the algorithms are implemented in Python through the Phoenix library. The boundaries of our domain are marked according to this figure. The conservation of mass is imposed by the continuity equation, and the conservation of linear momentum is imposed by the Navier-Stokes equations. The initial conditions for the velocity and pressure fields are null, and the initial shape of the interface is given by h of x, as presented here. Here, hc represents an undisturbed film thickness, epsilon is the perturbation amplitude, and lc is the perturbation wavelength. We have the following boundary conditions. For the interface, we have a kinematic boundary condition and the balance of stress along the interface. The interfacial tension is given by the constitutive equation shown here, and the interfacial viscosity is modeled by the Boussinesq-Scriven law. Left and right boundaries of the domain are artificial boundaries in which the flow is considered to be developed, and also the curvature of the interface in this region is minimal, resulting in the absence of pressure gradient on the y direction. The bottom boundary is the symmetry plane, in which the shear stress and the flow across the boundary are null. And here we have the residual equation, obtained by the weak formulation of our system of differential equations. We use the Galerkin method in our finite element formulation and triangular elements in our discretizations. We use quadratic elements for the velocity and linear elements for the pressure. The motion of the interface will be updated by the ALE method, and we implement the Newton-Raphson method to solve the resulting system of nonlinear algebraic equations. We will consider the linear stability criterion proposed by Ernest and Davis to analyze the results obtained from the inviscid interface case. This linear stability criterion considers the parameters S, which is the ratio between capillary forces and bulk viscous forces, and A, which is the ratio between van der Waals forces and bulk viscous forces. It states that, under this geometric restriction, the thin film is linearly stable if S over A is greater or equal to 2 over pi squared. We also consider these expressions for the characteristic scales of our problem and use the following dimensionless variables to present the results obtained. We also consider the capillary number and the Bushnell number on the discussion of the results presented in this work. The setup of the problem is defined according to these parameters and conditions. And so these are the results obtained from the inviscid interface case. And here we initialize our domain with a perturbation of amplitude equals to 2% of the undisturbed film thickness and a capillary number of 2. We represent the perturbation evolution in terms of the initial perturbation amplitude by means of the parameter epsilon. In this chart here, we have the evolution of the perturbation epsilon in x equals 0 for various values of S over A. And here we can see that for small values of S over A, the perturbation grows monotonically. Intermediate values of S over A leads to the retraction of the perturbation until a certain time, and then the perturbation grows afterwards, resulting in a non-monotonic behavior. For larger values of S over A, the retraction of the perturbation occurs until the film recovers a homogeneous thickness. And here we keep S over A equals to 1 over pi squared, and initial perturbation of amplitude equals to 10% of the undisturbed film thickness, and the capillary number equals to 2 for the following results. And here we see the evolution of the pressure field, and the pressure is maximum at the region of minimal thickness, which is located in x equals 0. The pressure increases in x equals 0 until the film reaches the rupture, resulting in an increase in the pressure gradient from x equals 0 towards the extremities. This increase of the pressure gradient influences the drainage of the liquid from the perturbed region. We see here the x component of the velocity field on the right figure, which indicates that the increase on the drainage velocity in time. The left figure shows the y component of the velocity field, in which we can see that the minimum value occurs in x equals 0. And also, the thickness of the film increases near x equals plus or minus 0.5, and this behavior may be related to the occurrence of capillary ridges. Now let's move to the results obtained for the viscous interface case. And here we keep the ratio S over A fixed in 1 over pi squared, the capillary number is fixed at 2, and we vary the Bushnell number between 0 and 75. The inviscid interface is given by the Bushnell number equals to 0. And the left chart presents the evolution of the perturbation epsilon in time for various values of the Bushnell number. And we see that as the Bushnell number increases, the perturbation evolution becomes slower. The right chart presents the rupture time as a function of the Bushnell number for values of the Bushnell number between 0 and 5. And we see that the effects of interfacial viscosity slows down the rupture process. And here we have the pressure field for 4 values of the Bushnell number. These results are evaluated at t equals 4.3, which is the rupture time of the inviscid interface case. Notice that the pressure distribution is similar in the cases with considerable interfacial viscosity, presented by the high Bushnell numbers. And here we see the x and y components of the velocity field at t equals 4.3 for 4 values of the Bushnell number, respectively on the left and right. We can notice on the left figure that the increase of the interfacial viscosity leads to a reduction on the drainage velocity. On the right figure, we see that the effects of interfacial viscosity reduce the velocity of attraction between the free surfaces, indicating that interfacial viscosity opposes the effects of the van der Waals forces. Okay, so we can conclude a few points with these results. For the inviscid interface, we remark that the linear stability criterion succeeds at predicting the early behavior of the system, but it fails after a given time. This is evident by the non-monotonic behavior observed in our results. And this failure may be associated with the linear nature of the criterion, in which nonlinear effects are not considered. And also, we observe that the effects of interfacial rheology strongly opposes the action of long-range intermolecular attraction between the free surfaces. At last, the effects of interfacial viscosity reduce the growth of the perturbation. For future works, we would recommend the evaluation of the perturbation evolution in viscous interfaces for different values of S over A. And we also recommend the execution of experimental works regarding thin films with viscous interfaces, as there are not so many works available in the literature. And with that, we finish the presentation, and I thank you very much.